What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. There is a smudge of light in the northern sky, on the border between two faint constellations, that you could pass 1,000 times through a telescope and never look at twice. It is not a star, although for years astronomers logged it as one. It is the glow of gas falling into something enormous, and that light has been traveling toward us for roughly 10 billion years. It left its source before the sun existed, before the earth had gathered itself out of dust. When you finally see it, you are not looking at an object. You are looking at a rumor of one. We have given that smudge a name, TON 618, and we have given it a title that sounds absurd for a thing no telescope has ever resolved. We call it one of the most massive black holes ever found, 66 billion times the mass of the sun. More than every star in the Milky Way added together, gathered into a single point you cannot see. And that is the strange part. Nobody has ever seen the edge of TON 618. No photograph of it exists. No telescope on Earth or in orbit can make out its shape. It is a dot. So here is the question this whole documentary is going to chase, and it is harder and stranger than it first sounds. If you cannot see a thing at all, how do you measure how big it is? And once you have measured it, how sure are you allowed to be that you have found the biggest one? Because the deeper you go into the record books of the largest black holes, the more you meet something that almost nobody says out loud. The biggest objects in the universe are the ones we have measured the least directly. The champion changes depending on whom you ask and which method they trust. And the single largest number you will find anywhere, a black hole of 100 billion suns, was never weighed at all. It was calculated. That is not a scandal. It is not scientists inventing things. It is something more interesting than that. It is what the true frontier of knowledge looks like up close, at the exact place where our ability to measure runs out. There is something almost primal about wanting to know the largest of a thing. The biggest animal, the tallest mountain, the deepest trench in the sea. Black holes are the ultimate version of that instinct, because they are the most extreme objects gravity is capable of making, the places where matter and space are pushed hardest against their own limits. To ask which black hole is the largest is really to ask how far the universe is willing to go, how much it will pour into a single point before something gives way. And the answer, as we are about to find, is tangled up with the equally strange question of how we could ever hope to know it. If that idea grips you the way it grips me, that the single largest object in the entire universe might be the one we have actually measured the least, and that the reigning record was never truly weighed at all, then consider subscribing. I make these documentaries for exactly that kind of turn, where a simple question quietly opens onto something far stranger, and having you along for the next one is the only support this really needs. So let me start with the surprise that reorganizes everything else, the one fact that has to come first. When an astronomer says a black hole is big, they are almost never describing something they can see. They are describing its mass, And the size of a black hole, the part we call its edge, is nothing more than its mass wearing a different coat. Here is what that edge really is. A black hole is a place where gravity has become so concentrated that to escape from close enough in, you would need to travel faster than light. And because nothing can travel faster than light, nothing escapes. There is a boundary around that point, an invisible surface, where the required escape speed reaches the speed of light exactly. Cross it going inward, and there is no path back out. Not for a spacecraft, not for a beam of light, not for any signal the universe allows. That surface is the event horizon. It is not a wall, and it is not made of anything. It is a line drawn by speed. It is the shape of no return. And the size of that boundary follows a beautifully simple rule. Double the mass, and you double the radius of the horizon. Triple the mass, triple the radius. The event horizon grows in direct proportion to how much you feed the black hole, and nothing else. That relationship even has a name. The distance from the center out to the horizon is called the Schwarzschild radius, after the physicist who first solved the equations for it while serving in the First World War. Run the numbers for familiar things, and the rule stops being abstract. If you could crush the entire sun down until it became a black hole, its event horizon would be a sphere about 3 kilometers across. Crush the whole Earth the same way, every ocean and mountain and molten layer, and the horizon would be smaller than a marble, about 9 millimeters wide. That is the true meaning of size for a black hole. It is not width, it is weight, translated into a radius. And once you understand that, the entire question of this documentary transforms into something you can actually attack. To find the largest black hole in the universe is not to find the one that looks biggest. It is to find the one that weighs the most. Everything now depends on a single skill: weighing a thing you cannot touch, cannot land on, and in most cases, cannot even see. Before we start lifting black holes onto the scale, there is one more twist about their size worth holding on to, because it overturns the way they are usually drawn. We picture the largest black holes as the most savagely destructive, cosmic shredders that would tear you apart the instant you came near. For small black holes, that picture is fair. For the giants, it is not. What actually tears things apart near a black hole is not gravity itself, but the difference in gravity between your feet and your head, a stretching we call the tidal force. And that difference is fiercest where the horizon is smallest and tightest. A black hole a few times the mass of the sun has a horizon only kilometers wide, and the tides just outside it would draw a human body into a thin thread long before it ever reached the edge. But a black hole of tens of billions of suns has a horizon so vast that the pull barely changes across the length of a person. You could, in principle, drift across the boundary of one of these monsters and feel nothing in particular at the moment you cross the line of no return. The largest black holes are not the most violent edges in the universe. They are the gentlest and the most quietly inescapable. Size, once again, is doing something to our intuition that we have to correct by hand. It also helps to know the family these record holders belong to, because black holes come in wildly different weights. The smallest ones we know of form when a single massive star runs out of fuel and its core collapses, and they weigh a few times to a few tens of times the mass of the Sun. These stellar black holes are scattered through every galaxy in their millions. At the other extreme sit the supermassive black holes, the ones anchored at the centers of galaxies, weighing from a few million to a few billion suns. Our own Sagittarius A star, at roughly 4 million, is a fairly modest member of that class. And then, at the very top, astronomers set aside a special tier for the true titans, the ones above about 10 billion solar masses. They call them ultramassive. Every object in this documentary's record chase, TON 618, Holmberg 15A, Phoenix A, belongs to that rarest tier. Strangely, there is also a gap lower down in the family. Black holes of a few hundred to a few thousand suns, the so-called intermediate mass black holes, are oddly hard to find, and for a long time were almost entirely missing from the catalog, a puzzle astronomers are still working to fill. So the range runs from a few suns to 100 billion, a span of more than 10,000 million-fold in mass, and everything we are about to weigh lives at the very extreme upper end of it, in the ultramassive tier, where both the objects and our uncertainty about them reach their maximum. And that top tier is genuinely rare. Ordinary supermassive black holes sit at the center of essentially every large galaxy, which means there are hundreds of billions of them scattered within reach of our telescopes. But the true titans, the ones pressing above 10 billion suns, are a tiny and exclusive club. You could very nearly count the strongest candidates on your fingers. They are not sprinkled evenly through the cosmos. They gather in the rarest, richest neighborhoods, the crowded hearts of the largest galaxies, and even there they are exceptional. So when we ask which is the single largest black hole in the universe, we are not sifting through a vast catalog of near equals. We are comparing a small handful of extreme objects, each one weighed by a different method, each carrying its own uncertainty, and trying to rank them across billions of light years. It is less like reading a leaderboard and more like judging a race whose runners are each in a different room, timed by a different clock. So let us do the thing that sounds impossible. Let us weigh a black hole. And to be fair, we should start with the one we trust the most, which happens to be the one hanging over your head right now, at the center of our own galaxy. Its name is Sagittarius A star, and for a long time it was only a suspicion. Something at the heart of the Milky Way was pouring out radio noise from a region no bigger than our solar system, and the obvious guess, a giant black hole, was exactly the kind of guess that is easy to make and very hard to prove. You cannot see it. The center of the galaxy is buried behind thick clouds of dust that block visible light completely. For most of the 20th century, the heart of our own galaxy was a locked room. The way in was not to look at the black hole. It was to look at the stars nearest to it and watch what they did. Two teams, one led from Germany and one from California, spent decades tracking a handful of stars in the crowded galactic center using infrared light, which slips through the dust that stops ordinary light. And they watched those stars move, not drift slowly the way stars usually seem to. They watched them race and curve and swing around an invisible point as if tied to it by an unbreakable thread. One star in particular, a blazing blue star we call S2, became the key witness. Astronomers followed it for a full loop of its orbit, and that orbit was astonishing. S2 swings around the invisible center once every 16 years, and at its closest approach, it is moving at nearly 5,000 kilometers every second, almost 2% of the speed of light. Something was flinging a massive star around a racetrack at a speed that only one thing could explain. Getting that orbit was not a matter of one clear night at a telescope. It was a marathon that ran for the better part of 30 years. The center of the galaxy is so blurred by the churning of our own atmosphere that early images smeared those stars into useless smudges. So astronomers had to wait for a technique called adaptive optics, in which a telescope's mirror is flexed hundreds of times every second to cancel out the shimmer of the air in real time. Year after year, two rival teams returned to the same tiny patch of sky and marked how far each star had crept, slowly tracing the loops by hand across decades. And in the spring of 2018, the patience paid a bonus. The star S2 came screaming through the closest point of its orbit, and as its light climbed back out of the black hole's gravity, the astronomers watched that light sag towards slightly redder colors, exactly the drain of energy that Einstein's theory predicts for a beam struggling up out of deep gravity. The orbit did not only weigh the black hole, it confirmed, right at the lip of the monster, that our theory of gravity still held. That is the kind of evidence that turns a suspicion into a foundation you can build the rest of the story on. And this is where the weighing happens, because an orbit is a scale. This is one of the oldest and most trusted tools in all of astronomy. If you can watch one object orbit another, and you can measure how wide the orbit is, and how long each lap takes, then the laws of gravity hand you the mass of whatever sits at the center. It is the same physics that lets us weigh the sun by watching the Earth go around it. There is nothing exotic about that step. It is more than 3 centuries old, the very law Isaac Newton wrote down to explain why the planets circle the sun. And it is beautifully strict. A wider orbit or a faster lap means more mass at the center, and the relationship is exact, not a loose trend you argue about. We use it to weigh the sun from the Earth's orbit, to weigh Jupiter from the motion of its moons, to weigh distant pairs of stars from the way they swing around each other. It never once requires us to see the central object. It only requires us to watch something held in its grip and to time the loop. That is why weighing Sagittarius A star from the orbit of a single star is the most trustworthy measurement in this entire subject. It leans on the best tested law in the history of physics, and it needs to see only the runner, never the thing at the center of the track. Point the method at the galactic center, feed in the size and speed of S2's orbit, and out comes a number that does not care about your opinion. The invisible thing at the heart of the Milky Way weighs about 4.3 million times as much as the Sun, packed into a region smaller than the orbit of Mercury. There is no other object that can be that heavy, that small, and that dark all at once. A cluster of dim stars would have been torn apart. A cloud of gas would have dispersed. Only a black hole survives the arithmetic. It is worth being careful right here. because a good scientist does not shout black hole the moment they find something heavy and invisible. For years, people asked whether the mass at the galactic center might be something less exotic, perhaps a dense swarm of dim, burned-out stars, perhaps a cluster of dead neutron stars, perhaps some ball of exotic particles, crammed together and simply too faint to see. The orbit of S2 is what closed those doors, one after another. To hold a star on a 16-year loop, swinging that fast at its closest approach, the central mass has to be not only enormous, but astonishingly concentrated, squeezed into a volume smaller than the orbit of a single planet. Any swarm of ordinary objects packed that tightly would collide, heat up, and either blaze into visibility or fling itself apart within a cosmic eye blink. It could not sit there, dark and stable, for the age of the galaxy. Once you demand that much mass in that little space, staying silent and staying whole, our physics leaves exactly one survivor standing: a black hole. That is how the case is actually built, not by leaping to the dramatic answer, but by ruling out every gentler one until only the monster remains. And so, by watching a star run its lap, we weighed the monster in our own basement without ever seeing it. Two of the astronomers who led that work, Reinhard Genzel and Andrea Ghez, shared the Nobel Prize for it. And there is a satisfying coda to that story, one that speaks directly to the whole theme we are chasing. Years later, in 2022, the same Event Horizon telescope that would soon become famous turned its planet-sized eye on the center of our own galaxy and captured the shadow of Sagittarius A star as well. Here was a second, completely independent way to weigh the same black hole, not by tracking the orbit of a star, but by measuring the size of the dark shadow the black hole casts on the glowing gas behind it. And the two methods agreed. The shadow gave a mass that matched the orbit, right around 4 million suns. When we can bring two honest, independent methods to bear on a single black hole, they line up. Hold on to that, because it is the quiet reassurance that makes the disagreements we are about to meet so revealing. The methods agree where we can check them against each other. The trouble begins precisely where we can only afford one. Hold on to that method, because it is the gold standard, and every weaker method we are about to meet will be measured against it. Watching a real object orbit and timing its lap is as close to putting a black hole on a scale as nature ever lets us get. The trouble is painfully simple. It only works when you can actually see individual objects looping around the black hole. And that is a privilege that runs out fast, almost as soon as we leave home. Not quite instantly, though, because there is one more nearly direct method worth meeting, and it happens to be the most precise of them all. In a small number of galaxies, there are clouds of water vapor orbiting close in to the central black hole, and under the right conditions, those clouds act as natural lasers, beaming radio waves at one exact frequency. The most celebrated example sits in a galaxy called NGC 4258. There, a disk of these water clouds circles the black hole almost perfectly edge-on, and radio telescopes can pick out individual bright spots in that disk, measure how fast each one is moving from the shift in its frequency, and even watch them creep along their orbits from one year to the next. It is very nearly like watching the orbit of the star S2, except the runners are glowing clouds of water, and the racetrack is a disk wrapped around a black hole, tens of millions of light years away. The result is the most accurate mass ever measured for any black hole beyond our own galaxy, pinned down to within a few percent, at around 40 million suns. But notice the catch that keeps coming back to haunt us. This exquisite method needs a rare, almost perfectly aligned disk of water lasers, and only a handful of galaxies in the whole sky offer one. It is breathtakingly precise, and it is nearly useless for the giants, because not one of the record holders happens to come gift-wrapped with a water laser disc turned conveniently on its edge. Now travel outward, about 55 million light-years, to a giant elliptical galaxy in the Virgo cluster called Messier 87. It is a very different animal from our own galaxy. It is vast and round and old, and from its core it fires a jet of glowing plasma, thousands of light years into space, straight and bright, like a searchlight aimed out of the galaxy. Something at the center is not just heavy, it is powerful. And this is the black hole that, in the spring of 2019, became the first one humanity ever photographed. The picture came from the Event Horizon Telescope, and it is worth understanding what that instrument really is, because it is one of the boldest measurements ever attempted. No single dish on Earth is large enough to see the edge of a black hole 55 million light-years away. The detail required is like standing in one city and reading a newspaper held open in another. So astronomers did something clever. They linked radio telescopes on mountaintops across the entire planet, from Hawaii to Spain to the South Pole, and combined their signals so precisely that together they acted as one telescope nearly the size of the Earth. That is what it takes to resolve a black hole. A dish the width of a world. And what they saw was not the black hole itself, because a black hole gives off no light. What they saw was a ring, a bright circle of hot gas, glowing as it swirls just outside the point of no return, with a dark round hole punched in the middle. That dark center is the shadow, the region where the horizon and the bending of light conspire to let nothing reach us. For the first time, a human being was looking at the silhouette of an event horizon. It is worth dwelling on what that ring actually is, because it is stranger than a simple circle of gas. Near a black hole, gravity bends the path of light so severely that some beams are curved right around the hole before they escape toward us. So part of what the telescope captured is not only gas beside the black hole, but light from behind it and around it, wrapped across the front like a halo. And the dark patch in the middle is actually larger than the event horizon itself, because that same bending of light magnifies the shadow, swelling it to a bit more than twice the true width of the horizon. We are not simply looking at a hole punched in a cloud. We are looking at the way a black hole folds the very paths of light around itself. And it is that fold, precisely predicted by the theory, that carries the measurement. The effort behind that single picture is almost as staggering as the picture itself, and it is a good reminder that these measurements are made by people, not by magic. Each telescope in the array recorded so much raw data that there was no way to send it over the internet. The observatories filled stacks of hard drives, thousands of them, and the drives were physically flown to 2 central sites to be combined, including a batch from the South Pole that could not even be shipped out until the Antarctic winter ended and the planes could land again. Then it took a team of more than 200 scientists and specially built software working for the better part of 2 years to turn that mountain of raw signal into one ring of light. When the image was finally revealed in the spring of 2019, it was not a photograph in the ordinary sense. It was a reconstruction, assembled with enormous care and cross-checked 4 separate ways so that no one team's assumptions could invent the ring on their own. This matters for our story because it shows the standard these scientists hold themselves to, even when the answer is a picture. Now watch what happens to that standard when the answer can only ever be a number. Now here is the measurement. The size of that dark shadow is not arbitrary. General relativity predicts, very precisely, how large the shadow of a black hole should be for a given mass. A heavier black hole bends light around a wider circle and casts a bigger shadow. So you measure the width of the ring in the photograph, you compare it against the theory, and the mass falls out. Point that method at Messier 87, and the answer comes back at about 6.5 billion times the mass of the Sun. A number read almost directly from a picture of the thing itself. It does not get much better than that. Except for one detail that most people never hear, and it is the detail this entire documentary turns on. Before the photograph, astronomers had already weighed the black hole in Messier 87 twice, using 2 other methods, and the 2 methods disagreed. One approach watched the motion of stars swarming through the galaxy's core and gave a mass of around 6 billion suns. Another approach watched the motion of glowing gas orbiting the center and gave a mass of only about 3.5 billion suns. Same black hole, same galaxy, 2 respected teams. And their answers differed by nearly a factor of 2. Sit with that, because it is the quiet engine of the whole mystery. This is a black hole we can photograph. It is one of the best studied objects in the sky, and even here, the number you get for its mass depends on how you choose to weigh it. When the Event Horizon Telescope image finally arrived, it landed close to the higher, star-based value, which was a genuine triumph and helped settle the argument. But the lesson underneath does not go away. A black hole's mass is not a fact you simply read off the universe. It is the output of a method. Change the method, and the number can move. And we have just been looking at the easy case. We have been looking at the black holes near enough to photograph or to watch stars orbit. There are only a few dozen of those in the entire sky. A few dozen galaxies close enough and aligned well enough for us to weigh their central black holes by watching things move. Every single one of them comes in at a few billion solar masses or less. If the story ended here, the largest black hole in the universe would be a modest headline, something like Messier 87 6 billion suns, photograph attached. But the record holders are not a few dozen light years down the road, where we can watch stars run their laps. They are billions of light years away, so far that their entire host galaxies are barely smudges, and no orbit and no shadow will ever be visible to us. To weigh those, to reach the true giants, we have to give up on watching things move. We have to learn to weigh a black hole using nothing but its light. And the reason that is even possible is that the largest black holes, when they are feeding, become the most violently bright objects in the entire universe. We call them quasars. Anton 618, the smudge we started with, is one of the brightest of them all. The story of how we worked out what quasars are is one of the great double takes in the history of science, and it is worth a moment because it explains why these objects fooled us for so long. In the late 1950s and early 60s, astronomers kept finding point, like sources of radio waves that, in an ordinary telescope, looked like nothing more than faint blue stars. They were even named for that disguise: quasi-stellar radio sources, star-like sources of radio, which is where the word quasar comes from. They looked like stars, so everyone assumed they were stars. Then, in 1963, an astronomer named Martin Schmidt spread the light of one of them into a spectrum and could not make the pattern of colors fit any nearby star at all. It only fit if that faint dot was being swept away from us by the expansion of the universe at an enormous speed, and that speed meant it was not nearby. It was billions of light years away. For a single dot to still look that bright across billions of light years, it had to be outshining an entire galaxy from a region no larger than our solar system. That was the moment the quasar was born as an idea, a star that turned out to be a monster wearing a star's clothes. Ton 618 is one of those monsters, and one of the most extreme examples ever cataloged. A quasar sounds exotic, but the machine behind it is almost simple. Take a supermassive black hole and pour gas onto it. That gas does not fall straight in. Like water spiraling toward a drain, it forms a flattened, whirling disk, and as it spirals inward, it is squeezed and sheared and heated by friction and by the ferocious gravity, until the inner regions glow at temperatures of hundreds of thousands of degrees. That glowing whirlpool is called an accretion disk, and it is one of the most efficient engines nature has ever built. Falling into a black hole, matter can release far more energy for its weight than the nuclear fusion inside a star. It is worth pausing on just how efficient, because it is the reason quasars can be seen clear across the universe. When hydrogen fuses into helium in the heart of the sun, it turns only about 0.7% of that matter into energy, and that thin trickle is enough to keep the sun shining for 10 billion years. Gas spiraling down toward a black hole can do far better than that. By the time it reaches the inner edge of the accretion disk, it may have converted something like 1/10 of its entire mass into light and heat, more than 10 times what fusion can manage. And it does this simply by falling. Nothing is being burned. The energy comes purely from the plunge, from matter surrendering the energy of its own motion as it is dragged inward and squeezed. That is why a region no larger than our solar system can outshine a galaxy of hundreds of billions of stars. It is the most powerful sustained engine known to physics, and it runs on nothing more exotic than gravity and falling gas. There is a further subtlety that even shapes the size of a black hole, and it is worth a brief detour because it comes back to matter for the giants. Black holes are not always simply sitting still. They can spin, and most of the big ones spin fast, set turning by the gas they have swallowed over billions of years, all arriving with a slight sideways swirl. A spinning black hole is a stranger thing than a still one. It drags the very space around it into a whirl, and it allows gas to circle closer before falling in, which wrings even more energy out of the infalling matter and pushes the efficiency of the engine higher still. Spin even changes the exact size of the point of no return, drawing the horizon inward compared to a still black hole of the very same mass. So when we translate a mass into a horizon, the way we did for TON 618, we are giving a rounded figure that a rapid spin would trim a little. Astronomers can sometimes read that spin from the fine details of the light coming off the inner edge of the disk, which is one more property of these objects we can pull out without ever seeing them directly. For our purposes, the point is simple. Spin makes a black hole a more efficient and more compact engine than the plain picture suggests, and the largest, oldest, most heavily fed black holes are exactly the ones most likely to be spinning close to their limit. A single feeding black hole, no larger across than our solar system, can outshine every one of the hundreds of billions of stars in its galaxy combined. That is what TON 618 is. Not a dark object, but a blaze. Its light pours out at something like 140 trillion times the brightness of the sun. If you swapped our sun for TON 618 and placed it where the nearest stars are, it would outshine the full moon. It is one of the most luminous single objects ever catalogued in the history of the universe. It is worth knowing how such a thing was even found, because its history is a small echo of the larger confusion. TON 618 was first recorded in the late 1950s in a survey of faint blue objects made at an observatory in Mexico, and at the time, it was nothing more than a dim smudge on a photographic plate, quietly assumed to be a star in our own galaxy. Only years later, once astronomers understood what quasars were, did anyone measure how far its light had been stretched by the expanding universe and grasp the truth. That faint plate smudge was not a nearby star at all. It was one of the most luminous objects in the known cosmos, shining at us across 10 billion years. The odd catalog name, TON 618, is simply its entry number in that old survey, a plain and forgettable label now fixed to one of the most extreme objects ever identified by our species. And there is something poignant hidden in that 10 billion-year-old light, once you know how to read it. We are not seeing TON 618 as it is now. We are seeing it as it was 10 billion years ago, when the universe was young and violent and awash in gas. That era, only a few billion years after the Big Bang, was the golden age of quasars. Galaxies were colliding almost constantly, funneling torrents of gas into their centers, and black holes all across the cosmos blazed as quasars far more often than they do today. TON 618 is a postcard from that age, one of the brightest beacons of the era when the giants did most of their growing. What has become of it since is a much quieter story. In the 10 billion years its light has been crossing space to reach us. The gas around it has largely been eaten or blown away, and the quasar has very likely gone dark, settling into a dormant, starving giant, not so different from the silent black hole at the center of our own galaxy today. So the blazing monster we so carefully weigh does not really exist anymore, not in the form we see. We are weighing a ghost, reading the mass of a fire that almost certainly burned out billions of years before the Earth had even formed. And the number we argue over is a number about the deep past, carried to us by light that has outlived the very thing that made it. And that ferocious brightness, that beacon we can see across 10 billion light years, is exactly the thing that lets us weigh the beast hiding inside it. Because hidden in the light of a quasar is a motion we can read, even from the far side of time. But brightness on its own is a trap, and it is worth pausing to see why, because it explains everything that follows. It is tempting to assume the brightest quasar must hide the biggest black hole, as if we could simply rank the giants by how fiercely they glow. That does not work. How brightly a quasar shines depends mostly on how fast it happens to be feeding at that moment, not on how massive the black hole is. A modest black hole gorging on a sudden flood of gas can briefly outshine a far larger one that is sipping quietly. Brightness tells you about the meal, not about the diner. So to weigh the black hole itself, we cannot just measure how much light pours out. We have to find something inside that light that answers to the black hole's gravity, some motion that betrays the mass, whether the feeding is frantic or calm. And the light does carry exactly that. Here is the trick, and it is genuinely beautiful. A quasar does not shine steadily. The gas falling in is turbulent, so the light from the very center flickers, brightening and dimming over days and weeks. Now, surrounding that blazing core, farther out, there are enormous clouds of gas, and those clouds glow only because the core is lighting them up. So when the core flickers, the clouds flicker too. But not at the same instant. The clouds are farther out, so the light has to cross the gap to reach them, and their echo of the flicker arrives late. Watch the core brighten today, and you might see the surrounding clouds brighten a few weeks from now. That delay is a ruler. If the echo takes, say, 20 light days to arrive, then the clouds must be sitting about 20 light days out from the black hole, because that is how far light travels in that time. We have just measured the radius of the gas, not by seeing across the distance, which is impossible, but by timing an echo. Astronomers call this reverberation mapping, and the word is exactly right. It is echolocation, done with the flicker of a dying star's worth of gas across the width of a galaxy. This is not a thought experiment. It has been done, patiently, for decades. Beginning in the 1990s, astronomers started staring at particular nearby feeding black holes night after night, month after month, year after year, logging every flicker of the core, and then waiting out the delay for the surrounding gas to answer. It is slow, unglamorous work. A single solid measurement can take years to pin down, because you have to catch the core brightening and then wait for the echo to arrive before you can measure the gap. But the reward is a real ruler laid against a black hole, and by now, dozens of them have been mapped this careful way. Those dozens matter enormously to the rest of our story, because they became the calibration sample, the trusted foundation on which every shortcut is built. They are the black holes we weighed the honest way precisely so that we could learn how to guess at the ones too far to reach. Keep that in mind. Every headline mass for a distant quasar ultimately leans on this small, hard-won collection of patiently monitored nearby black holes. Now we have the radius of the orbiting gas. We need one more thing to weigh the black hole, and it is the speed of that gas, which the light hands us for free. When we split a quasar's light into its spectrum, the glow from those clouds does not sit at a single sharp color. It is smeared into a broad band, because some of the gas is racing toward us, and some is racing away, and that motion shifts the color of the light, stretching it one way and squeezing it the other. The wider that smear, the faster the gas is moving. So the spread of colors in the spectrum is a speedometer for gas we can never resolve as anything but a point. And now we are back on the firmest ground in astronomy. We have a radius from the echo. We have a speed from the spread of color. Radius and speed around a central mass are exactly what we used to weigh Sagittarius A star by watching the star S2. The same law of gravity applies. Feed in the radius and the speed, and the mass of the black hole falls out. We have weighed a black hole billions of light years away, using nothing but the timing of its flicker and the width of a color. That is not a trick of imagination. It has been done, carefully, for hundreds of feeding black holes, and where we can cross-check it against other methods, it holds up. But there is a catch waiting, and it is the catch that lets the giants slip loose. Reverberation mapping needs patience. You have to watch a quasar for months or years to catch its flickers and their echoes. And for the most distant monsters, that patience runs into a wall built by the universe itself. Ton 618 is so far away that its light is stretched by the expansion of space, which stretches its clock too, so its flickers appear to us slowed and smeared. It is faint in the ways that matter and its echoes would take a human career to map. For the true record holders, the full echo method is often a luxury we cannot afford. So for objects like Ton 618, astronomers fall back to a faster, cheaper version of the same idea. And this is the exact moment the certainty starts to leak out of the numbers. Instead of monitoring the quasar for years to measure the radius of the gas by echo, they take a single snapshot of its spectrum, one night's light, and they estimate the radius a different way. It turns out that brighter quasars tend to have their glowing gas clouds farther out, and astronomers have measured that relationship using the closer quasars they could map properly. So they measure how bright Ton 618 is, use that relationship to guess the radius, read the speed of the gas from the width of the spectral line, and combine the two into a mass. This shortcut has a name too. It is called the single epoch method, and almost every headline mass for a distant giant, including Ton 618, comes from it. Notice what just happened. In the echo method, the radius was measured. In this shortcut, the radius is inferred from a general trend applied to an object far larger and farther away than anything the trend was built on. The speed is still real, read from the light. But one of the two ingredients has quietly changed from a measurement into an estimate. And estimates carry a spread. You can see that spread directly in the history of TON 618 itself. The famous number, 66 billion solar masses, comes from an analysis published in 2004, based on the width of one particular emission line from hydrogen, but a later study, using a more careful treatment of the same kind of data, revised the figure downward to about 40.7 billion. Same quasar, same blazing light, two capable analyses, and the mass moved by a third, roughly 25 billion suns of difference, which is to say, it moved by more than the mass of every star in a large galaxy, purely because the method was refined. Nobody did anything wrong. This is simply how much room lives inside the shortcut. It helps to see exactly where that room comes from, because it is not vagueness, it is a specific and honest problem. The width of a spectral line is our speedometer for the gas, but a quasar does not offer just one line to read. Its light carries several, produced by different elements, and crucially, by gas sitting at different distances from the black hole. A line from hydrogen may come from gas at one radius. A line from magnesium may come from gas somewhat farther out. A line from carbon may come from gas farther out still, and blown around by fierce winds that are not purely tracing gravity. Each line reports a slightly different speed and implies a slightly different radius, so each line hands back a slightly different mass. For the closest, best behaved black holes, these all agree well enough to trust. But for a remote monster like TON 618, which line you can even see at all depends on how far the expansion of the universe has stretched its light, and the line that happens to be visible is not always the most reliable one. The famous 66 billion figure and the revised 40 billion figure are, in large part, the sound of careful astronomers disagreeing about which line to trust and how to correct it. Neither side is being sloppy. They are both being honest about a genuinely hard measurement, and the honest result is a number with real width built into it. And yet, even the low end of that range is almost incomprehensible. And this is where I want to stop and let the sheer scale land, because it is genuinely one of the most staggering facts in astronomy. Take the famous figure, 66 billion suns, and turn it into a size using the rule we learned at the start. Double the mass, double the horizon. At 66 billion solar masses, the event horizon of TON 618 is a sphere roughly 1,300 astronomical units across. An astronomical unit is the distance from the Earth to the Sun. So we are talking about a boundary more than 1,000 times the distance from here to the Sun. To feel that, put our whole solar system inside it. From the Sun out to Neptune, the edge of the planets is about 30 astronomical units. The event horizon of TON 618 is more than 1,000. You could line up our entire planetary system, Sun to Neptune, roughly 40 times across the diameter of this single black hole, and still not span it. Light itself, the fastest thing there is, would need about 2 weeks just to cross from one side of the horizon to the other. And the glowing accretion disk feeding it is larger still, wider than a light year, a whirlpool of superheated gas broad enough to swallow the distance to the nearest stars. And try, for a moment, to feel the mass itself, not just the size. 66 billion suns is a number so large it simply slips through the fingers. If you tried to count to 66 billion out loud, one count every single second, without ever sleeping or stopping, you would not come close to finishing in a human lifetime. You would need more than 2,000 years. Now make each of those counts an entire sun, a ball of fire more than 1,000,000 kilometers across, and gather every one of them into a single dark point smaller than the room our planets move in. That is the thing we are weighing. Not merely a heavy object in the ordinary sense, but the mass of a substantial galaxy's worth of stars, folded down into one silent knot of gravity at the far edge of time. That is the champion as the record books usually print it, a single dark boundary, 1,000 times the width of the Earth's orbit, hidden inside a beacon that outshines a galaxy, 10 billion years back in time. It is the kind of object that makes the word big feel like a failure of language. To make that size felt, hold it against the black hole we started this journey with, the one in our own galaxy, Sagittarius A star, at 4 million suns, has an event horizon you could tuck comfortably inside the orbit of Mercury. It is a giant by any human standard, and yet TON 618 dwarfs it so completely that the comparison almost stops meaning anything. If you shrank TON 618 until its event horizon was the size of a city, then Sagittarius A star, on that very same scale, would be smaller than a single grain of sand lying at the edge of that city. That is the leap from an ordinary supermassive black hole to a true ultramassive one. And we measured that leap, remember, not by seeing either edge, but by reading the color of light that left one of them 10 billion years ago. But we have arrived at the champion by the least direct road we have traveled yet. We could not watch a star orbit it. We could not photograph its shadow. We could not even time its echoes. We measured its brightness, borrowed a relationship from smaller quasars, and read a speed from a smear of color. And when we did, the number wobbled by 25 billion suns, depending on who ran the analysis. So a fair mind has to ask the uncomfortable question. If the most famous giant is measured this loosely, is it even the real record holder? And what is the largest black hole we have ever weighed the honest way? By watching something move. For that, we go to a galaxy called Holmberg, 15A, about 700 million light-years away. It is the brightest galaxy at the center of a great cluster of galaxies named Abel 85, and it is a strange and revealing place. Its very core is not a bright pileup of stars, the way most galaxy centers are. It is scooped out, dim, oddly hollow, as if something had carved a cavity in the middle of a city and left the streetlights thin. That hollow core is a fingerprint, and the suspect that leaves it is a truly enormous black hole. And the way that fingerprint is made tells us something about how the giants grow. When two galaxies merge, and large galaxies grow largely by merging, the big black hole at the center of each one sinks toward the middle of the combined galaxy, and the two black holes end up orbiting one another. As that pair spirals slowly inward, it behaves like a colossal set of egg beaters, flinging away any star that wanders too close through the slingshot of their combined gravity. Over time, this evicts the stars from the very center and leaves behind exactly the kind of scooped-out, dim core that Holmberg 15A shows us. The size of that excavated region even scales with the mass of the black holes that carved it, so the emptiness itself becomes an independent clue to how heavy the central engine is. In other words, the largest black holes carry a record of their own violent history written into the starlight around them. Holmberg 15A did not simply grow fat by sipping gas over the ages. It very likely swallowed at least one rival black hole in a merger of giants, and the scar of that collision is the hollow at its heart. There is a pattern worth naming in where these titans are found, because it is a clue to how they are built. The two heaviest black holes in this whole story, the ones in Holmberg 15A and in Phoenix A, are both the central engine of the brightest galaxy at the heart of an enormous cluster of galaxies. That is not a coincidence. Clusters are the largest structures gravity has ever assembled. Great cities of hundreds or thousands of galaxies bound together. And the galaxy that settles at the very center of a cluster becomes a kind of cosmic drain. Over billions of years, other galaxies sink toward that center and are swallowed, and every one of those mergers delivers another central black hole to join the one already waiting. The brightest cluster galaxy grows into a monster by devouring its neighbors, and its black hole grows in exactly the same way, merger upon merger, until it stands among the largest objects in the universe. So if you want to hunt for the true record holder, you do not scan the sky at random. You look straight at the hearts of the greatest clusters, because that is where the universe stacks its mass the highest, and where the giants are forged. It is precisely where both Holmberg 15A and Phoenix A are found. Holmberg 15A is too far away to watch a single star orbit its center the way we watched S2 in our own galaxy. But there is a middle path between tracking one star and giving up entirely, and it is more direct than reading a quasar's light. You cannot follow one star there, but you can measure the collective motion of the whole swarm of stars in the galaxy's core, how fast, on average, they are buzzing around. Then you build a detailed computer model of that core, a model containing millions of possible stellar orbits, and you ask which arrangement of orbits, around which central mass, reproduces exactly the motion you observe. The stars are still doing the weighing. You are just reading the crowd instead of one runner. In 2019, a team used one of the great telescopes in Chile to do precisely that, and the answer was the largest black hole mass ever obtained by directly watching things move, about 40 billion times the mass of the Sun, not inferred from brightness, not borrowed from a trend, measured from the motion of stars. For the first time, the honest, gold standard method had reached up into the tens of billions, into the same territory as the quasar giants, and it planted a flag there at 40 billion suns. And then, just as you would now expect, the flag moved. In a newer analysis, a different team modeled the same galaxy with a more flexible, more realistic geometry for how those stellar orbits are arranged, and their answer for the very same black hole came out at around 22 billion solar masses. Once again, same object, same careful craft, and the number nearly halved when the model grew more sophisticated. Even at the gold standard, even watching real stars move, the mass of the largest black holes carries an uncertainty of roughly a factor of 2. Let me gather what we have found, because a pattern has been quietly assembling itself, and it is worth saying plainly. Every time we weigh a black hole, the number depends on the method. Near home, watching one star, we get 4 million suns, and we trust it completely. In a photographed galaxy, the star-based value and the gas-based value differed by a factor of 2 before the picture settled it. In the largest directly weighed giant, the honest method still swings between 22 and 40 billion. And in the famous Quasar, weighed only by its light, the figure floats between 40 and 66 billion. It grows, steadily and predictably, as the black holes get bigger and farther and darker, because the bigger they are, the less directly we are able to weigh them. Which brings us, finally, to the number that sits at the very top of the list, the 100 billion suns. The reigning heavyweight champion of the universe, a black hole often named as the largest of them all. It lives at the heart of a distant galaxy cluster, and it is called Phoenix A. And it is the perfect place to end the climb, because of how its record was set. Phoenix A was never weighed by watching a single star. Its shadow has never been photographed. No echo of its flicker has ever been timed. Its mass of 100 billion suns was not measured at any telescope. It was calculated. Here is where that number comes from, and it is not sleight of hand. It is a real and respectable tool pushed to its limit. Over the last few decades, astronomers noticed something remarkable. The mass of the black hole at the center of a galaxy is tightly related to the galaxy around it, in particular to how fast the galaxy's stars are collectively moving. Stir a galaxy faster, and you reliably find a heavier black hole at its heart. This link is so consistent across so many galaxies that it appears the two grow up together, the black hole and its galaxy shaping each other over cosmic time. This relationship was one of the great surprises of astronomy at the turn of the millennium. Around the year 2000, two separate teams found that the mass of a central black hole tracks the collective motion of the stars in its host, with startling tightness, far tighter than anyone had any right to expect for two things so wildly different in scale. Think about how strange that is. The black hole is a tiny speck compared to its galaxy. Its gravity directly rules only a region millions of times smaller than the galaxy around it, and the great majority of those stars are so far from the black hole that they have no idea it is even there. And yet, their average speed and the black hole's mass rise and fall together, in lockstep, galaxy after galaxy. The most natural reading is that the black hole and the galaxy did not grow up as strangers. They grew up entangled, feeding and starving each other through the same floods of gas and the same bursts of star formation until their fates were welded together. That idea, the co-evolution of black holes and galaxies, has become one of the central themes of modern astrophysics. And it is exactly what makes the relationship usable as a scale, because it means the galaxy carries, in the motion of its stars, a kind of memory of the black hole buried at its core. And it is useful, because it means that if you can measure how vigorously a galaxy is stirred, You can estimate the mass of the black hole you cannot see, without ever weighing it directly. Phoenix A sits inside one of the most massive, most luminous galaxy clusters we know, an environment so extreme that its central galaxy is a genuine monster. The Phoenix cluster is famous for exactly that extremity. At its heart, gas is cooling and crashing down onto the central galaxy so rapidly that the galaxy is igniting new stars at a furious pace, one of the most intense bursts of star formation ever seen at the core of a cluster. This is a place running at the very limits of what galaxies do, and it is precisely the kind of extreme host in which the scaling relation predicts an extreme black hole. Feed the properties of that colossal galaxy and its cluster into the relationship, and the formula predicts a central black hole of around 100 billion solar masses. That is the record. It is not a lie, and it is not a guess in the careless sense. It is an honest extrapolation. But it is an extrapolation, a prediction made by pushing a reliable trend out past the last place we were ever able to check it, into a regime no direct measurement has ever reached. The champion of the universe holds a title awarded by a correlation, and there is a specific reason to be careful about trusting that correlation at the very top. A relationship measured across ordinary galaxies is on solid ground in the middle of its range, where we have thousands of examples to check it against. But Phoenix A sits far out at the extreme edge, heavier and more exotic than almost anything that went into building the relationship in the first place. Out there, we simply do not know whether the trend continues straight, or bends upward, or bends downward, or scatters wildly, because we have so few directly weighed giants to test it against. Using it to crown a champion is a little like measuring the heights of everyone in a single town, drawing a neat line through the numbers, and then using that line to predict the height of the tallest person on the entire planet. The prediction is reasonable. It is also exactly the kind of confident extrapolation that can go badly wrong at the very tip, which happens to be precisely where the record lives. And that, finally, is the shape of the whole record book, seen clearly. As you climb from 4 million suns to 6 billion to 40 billion to 100 billion, you are not just climbing in mass. You are climbing down a ladder of certainty. Each rung up in size is a rung down in how directly we know the number. The largest black hole in the universe, as printed, is not the best measured object in astronomy. It is very nearly the least measured. And there is one more reason to hold that 100 billion figure at arm's length, a reason that comes not from the limits of our telescopes, but from the physics of the black holes themselves. Because there may be a ceiling, a mass that a black hole simply cannot climb past, and the record holders are pressing right against it. To see where that ceiling comes from, you have to understand that a black hole is a surprisingly clumsy eater, and the clumsiness gets worse the more it eats. Go back to the accretion disk, that whirlpool of superheated gas. As gas falls in and blazes, it pours out light, and light is not weightless in its effects. Light pushes. A stream of radiation striking gas exerts a real outward force on it. So a feeding black hole sets up a tug of war. Gravity pulls fresh gas inward, trying to feed the hole. The radiation from the gas already falling in pushes the next wave of gas back out. And here is the key. Past a certain feeding rate, the outward push wins. The black hole shines so fiercely that its own light blows away the meal before it can arrive. This balance point has a name. It is called the Eddington limit, and it sets the maximum rate at which a black hole can steadily feed, given its mass. A black hole cannot simply gorge as fast as it likes. Try to force gas in faster than the limit allows, and the resulting glare drives the surplus away. It is as if the act of eating produces a wind that clears the table. This does not make growth impossible, but it makes it slow and self-throttling. A black hole feeding at its limit still takes tens of millions of years to double, and every time it grows, the amount it must swallow to grow again gets larger. Now push that logic to the extreme, to the realm of tens of billions of suns, and something more severe kicks in. In 2009, two astronomers, Priyamvada Natarajan and Ezequiel Treister, worked out what should happen to the very largest black holes, and they found a natural wall. To keep feeding a black hole that is already 10 or 20 billion solar masses, you need an accretion disk so large and so heavy that the disk itself becomes unstable. Its outer parts, instead of calmly feeding the black hole, break up under their own gravity and collapse into stars, spending the gas on starlight rather than delivering it to the center. The supply line converts itself into a nursery and never reaches the hole. The black hole, in effect, starves itself by growing too big to be fed. The mass where this happens, where a black hole can no longer sustain its own growth, lands somewhere around 10 billion suns. And depending on the galaxy, it might stretch to a few tens of billions, but not far beyond. That is the theoretical ceiling, and you can already feel the collision it creates. The largest black hole we have ever directly weighed, in Holmberg 15A, sits at 22 to 40 billion, at or just above that predicted wall. The famous Quasar, Ton 618, comes in between 40 and 66 billion, higher still. And the reigning champion, Phoenix A, is printed at 100 billion suns, which is several times past where the physics says a black hole should be able to grow. So we are left holding two facts that do not want to sit together, and this is the honest heart of the whole subject. On one side, the record book says the largest black holes reach many tens, even 100 billion solar masses. On the other side, our best physics for how black holes feed says they should choke off their own growth, somewhere around 10 billion. Both cannot be fully right, as stated. Either the biggest masses are overestimated, exactly as the loose, indirect methods would allow, and the true giants are smaller and closer to the ceiling than the headlines claim. Or those giants are real, and our theory of how black holes stop growing is missing something important. The tension is not resolved. It is one of the live, open arguments at this edge of astrophysics, and anyone who tells you it is settled is selling certainty the evidence does not support. There is, though, a serious way to ease part of that tension, and it carries us back to the mergers we met earlier. The feeding ceiling near 10 billion suns applies to growth by accretion to a black hole fattening on gas, because it is the radiation from that gas that finally drives the next meal away. But mergers do not play by that rule at all. When two black holes at the centers of two colliding galaxies spiral together and combine, their masses simply add. There is no accretion disk to blow away, no radiation pressure to fight, no feeding limit in sight. Two black holes of 30 billion suns apiece can merge into one of 60 billion without breaking any feeding rule, because nothing is being fed. And this matters enormously for exactly the objects we have been chasing, because Holmberg 15A and Phoenix A both sit at the centers of great clusters, the very places where mergers of giant galaxies and of the giant black holes inside them happen most often of all. So it is entirely possible that the true record holders climbed past the accretion ceiling not by eating more, but by colliding and combining over and over in the crowded hearts of clusters. That would let a black hole exceed the feeding limit completely honestly, and it would mean the ceiling is real, but simply does not govern the whole story. Whether mergers can account for the full mass of the very largest giants, or whether the printed numbers are still too high even for that, is one of the open threads researchers are pulling on right now. There is even a third possibility, more speculative than the other two, that some physicists take seriously enough to explore. What if the very largest black holes did not grow by feeding at all, and so were never bound by the feeding ceiling in the first place? In the extreme conditions just after the Big Bang, it is at least conceivable that certain regions of the infant universe collapse directly into black holes, born already enormous, without ever passing through a star or an accretion disk. Black holes made that way are called primordial, and a handful of researchers have gone so far as to ask whether stupendously large ones, far heavier than any feeding process could ever build, might be hiding in the cosmos. It has to be said plainly that there is no direct evidence any such object exists, and this remains a fringe idea rather than an established one. But it makes a fair point. A limit on how fast a black hole can eat is not automatically a limit on how large a black hole can be, if nature has some other way of making them. So the record is uncertain from both ends at once. We are unsure how heavy the known giants truly are, and we are unsure what the real limit even is. And if you think that is a satisfying puzzle, the universe has one more twist waiting, because it turns out that reaching even 10 billion suns is hard to explain in the first place, not because of the ceiling, because of time. When we look at objects billions of light years away, we are looking into the past, because their light has taken billions of years to reach us. Point our telescopes far enough, and we are seeing the universe as it was in its first billion years, freshly lit. And when the James Webb Space Telescope turned its infrared eyes on that early era, it found something that has genuinely unsettled the field. It found black holes that were already huge, feeding as bright quasars, when the universe was only 500 to 700 million years old. Some of them already carried the mass of millions, or even a billion suns, and a few appear startlingly heavy compared to the small galaxies around them, as if the black hole had arrived before the galaxy was ready for it. Run the clock backward, and the problem is stark. We just spent a whole chapter watching how slowly black holes are forced to grow, throttled by the Eddington limit, able to double their mass at most about once every 40 million years, even when feeding flat out. Start from the kind of seed a dying star leaves behind, a black hole of a few tens of suns, and to climb all the way to 1 billion suns, you must double more than 20 times over, one doubling after another, with never a pause and never a slip below the maximum rate. String those doublings together, and the journey takes close to 1 billion years of perfect, uninterrupted feeding. But the quasars the James Webb Telescope is finding were already blazing at 1 billion suns when the universe was only 500 to 700 million years old, younger than that climb should even take. There are simply not enough doublings in the time available. The early giants should not have had time to exist, and yet there they are, a light in the infant universe. So astronomers are being pushed toward a different origin story for the monsters, one where they did not start small. Instead of beginning as the corpse of a single star, some of these black holes may have been born from the direct collapse of an enormous cloud of gas in the early universe, skipping the star stage entirely and forming a seed already weighing tens or hundreds of thousands of suns. A head start like that, hundreds of thousands of suns at the very beginning, gives the black hole enough doublings to reach the giants we see. Others may have fed in brief, violent bursts that broke past the ordinary Eddington limit in the dense, gas-rich conditions of the young cosmos. The debate is wide open, but the direction is clear. The largest black holes may not be the end product of patient growth at all. They may have been big from almost the very start, seeded huge in a universe that no longer makes seeds that way. It is worth being concrete about how such a head start could happen, because the leading idea is genuinely strange and beautiful. In the very early universe, before stars had seeded space with heavier elements, there were vast clouds of pristine hydrogen. Normally, a cloud that large would cool, fragment, and shatter into a swarm of ordinary stars. But under the right conditions, kept warm by the right kind of radiation from neighboring regions, such a cloud could refuse to fragment and instead collapse almost as a single body, funneling an immense amount of gas into one place at one time. The result would be a seed of perhaps 100,000 solar masses, forming nearly all at once, already far heavier than anything the death of a star could leave behind. Give a seed like that the full stretch of early cosmic time and even the ordinary feeding limit, and it can plausibly climb to the billion solar mass quasars we actually see. Meanwhile, the James Webb Telescope has been turning up a strange population of small, intensely red dots scattered across the early universe, and many of them look like exactly this: young galaxies whose central black holes are startlingly heavy for the modest starlight around them. If those readings hold, they are snapshots of the giants while they were still young, already massive before their galaxies had caught up. The record we chase today may simply be the grown version of these infant monsters, and how they were born is now one of the hottest questions in all of astronomy. This also loops straight back to that curious gap we noticed early on, the near absence of medium-sized black holes of a few hundred to a few thousand suns. If the giants had grown from ordinary stellar seeds, climbing the ladder one rung at a time, we would expect to find plenty of half-grown black holes stuck in that middle range. Their strange scarcity is another quiet hint that the largest black holes did not climb the ordinary way at all, but started high, from heavy seeds, and raced upward before their galaxies had finished forming. The missing middle and the impossibly early giants may turn out to be two faces of the very same clue, both pointing toward an origin we are only now beginning to piece together. There is one more twist from the early universe that sharpens the puzzle even further. In many of these young systems, the black hole is not merely large, it is too large for the galaxy around it. Normally, remember, a black hole's mass and its galaxy's stars keep careful pace with each other, bound by that tight relationship we leaned on to weigh Phoenix A. But some of the earliest black holes appear to break it, weighing far more than their scrawny young host galaxies have any right to allow, as if the black hole sprinted ahead while the galaxy is still struggling to catch up. Astronomers call these overmassive black holes, and they hint that in the very beginning, the black hole may have come first, seated heavy and growing fast, with the galaxy assembling around it afterward, rather than the two rising together as equals. It is a strange inversion of the familiar story, and one of the freshest puzzles the new telescopes have dropped in our laps. It also quietly raises the stakes on our whole question, because if the giants were already near their staggering masses when the cosmos was young, then the true record may have been set long ago, in an age we can barely glimpse, and everything since has been the slow cooling of a fire that was lit almost at the very beginning of time, which quietly reframes the record we have been chasing. The largest black hole in the universe is not just a question of which number is biggest today. It is a question about how the universe managed to build such things at all, so early, and whether it built a few of them right up against a wall that our physics says should exist. So let us answer the question we started with, as honestly as it can be answered, and then let us see what the answer has really given us. What is the largest black hole in the universe? If you demand a single name for the record book, the usual answer is Phoenix A, at about 100 billion times the mass of the Sun. But you now understand that this figure is a calculation, an educated extrapolation from the size of its galaxy, and that it sits well beyond the point where our physics expects a black hole to be able to grow. If instead you ask for the largest black hole we have genuinely weighed by watching light or matter respond to its gravity, the honest answer is a range, not a point. The famous quasar TON 618, read from its own blazing light, lands somewhere between 40 and 66 billion suns. The largest one measured the gold standard way, by the motion of stars, is the black hole in Holmberg 15A, and even it slides between 22 and 40 billion depending on how carefully you model it. Put those together, and the truthful headline is this: the largest black holes in the universe are objects of a few tens of billions of solar masses, crowding against a theoretical ceiling somewhere near 10 billion, and the precise identity of the single largest, along with its exact mass, is not something we currently know. The record is not a fact carved in stone. It is a frontier, and it is still moving. And it may be moving toward an answer we can never fully reach, which is worth admitting plainly. Everything we have weighed tonight, we could weigh only because it announced itself as a blazing quasar, or a photographed shadow, or a galaxy whose stars we could measure. But the largest black hole in the universe might do none of those things. It might be dormant, and dark, sitting in silence at the center of some galaxy we have never singled out, giving off no quasar light and swallowing nothing that would betray its size. It might lie so far away that its light has not had time to reach us in the entire history of the universe, forever beyond the edge of what we can see. When we crown a champion, then we are really only crowning the largest black hole we have managed to notice and to weigh, which is not at all the same thing as the largest that exists. The true record holder may be a quiet giant we will never point a telescope at, its mass known only to the galaxy it silently governs. That gap between the largest we can find and the largest that is one the universe may simply never let us close. If you want one clean way to carry this out with you, hold on to two numbers and the gap between them. The largest black hole we have ever weighed by directly watching matter respond to its gravity is around 40 billion suns, and even that figure may really be closer to 20. The largest number anyone actually prints, 100 billion, belongs to an object no one has ever weighed at all. The truth of the record lives somewhere inside that gap, between what we have measured and what we have only calculated, and closing it is the work that still lies ahead. And if a single moving number feels unsatisfying, sit with why for just a moment, because it is one of the most honest things in this whole story. Almost everything at the true edge of science looks like this. Not a clean fact stamped on a page, but a best estimate with a range around it, a number attached to a method and a set of assumptions, waiting for a sharper measurement to tighten it or overturn it. The mass of the largest black hole is uncertain for the very same reason the frontier is thrilling. We are asking a question right at the limit of what our instruments can do, about an object right at the limit of what physics can build. A confident single number in that place would not be knowledge. It would be a guess wearing the costume of certainty. The range is not the science failing. The range is the science being honest about exactly how far the light has carried us, and not one step further. And think how strange that contrast really is. We have weighed our own sun to many decimal places, and we can predict an eclipse to the second 1,000 years from now. Yet the mass of the largest black hole in the universe we know only to within a factor of 2, and the identity of the true record holder we do not know at all. That is not because black holes are somehow unknowable in principle. It is because these particular ones sit at the farthest, faintest, most extreme corner of everything we are able to reach, where even our cleverest instruments are working at the very edge of what they can do. Now here is what that long climb was really for, because it gives you something larger than a number. Look back at the ladder we climbed. 4 million suns at the center of our own galaxy, weighed by one star and trusted absolutely. 6 billion in a galaxy we photographed, argued over by a factor of 2 until the picture arrived. 40 billion in a distant giant, weighed by a crowd of stars and still uncertain by half. 66 billion in a quasar, red from a smear of color across 10 billion years. 100 billion in a champion that was never weighed at all. Notice the shape of that. As the black holes grew larger, our certainty about them grew smaller. Size and confidence ran in opposite directions the entire way up. In the universe, The biggest things are very nearly the least known things, not because we are careless, but because bigness pushes them into the dark, far away, unresolvable, weighable only by the faint tricks of light and inference. That is the real prize hidden inside this question, and it is stranger and better than any single record. A black hole's mass is not something you read off the sky like a temperature. It is the answer to a method, and the grander the black hole, the more the method has to lean on assumption instead of sight. That is why the champion keeps changing, why the numbers wobble by tens of billions of suns, why the crown belongs 1 year to a quasar and the next to a formula. We are not watching scientists fail. We are watching them work honestly at the exact place where measurement thins into inference and refusing to pretend the line is sharper than it is. And before we close, it is worth asking why any of this matters beyond the thrill of a record, because the answer turns these giants from a curiosity into something that reaches all the way down to us. For a long time, the black hole at the center of a galaxy was thought to be almost irrelevant to the galaxy itself, a tiny speck in a vast city of stars, far too small to matter. That view has collapsed. We now understand that when these black holes feed and blaze as quasars, they can pour out enough energy to reshape their entire galaxies, heating and driving away the very gas that would otherwise collapse into new stars. A large enough black hole, feeding hard, can effectively switch off the birth of stars across a whole galaxy, helping to decide whether that galaxy keeps growing or falls quiet forever. That tight link we found earlier between a black hole's mass and the motion of its galaxy's stars is the fossil left behind by this relationship. So the largest black holes are not passive giants resting at the bottom of a gravitational well. They are among the most powerful regulators in the entire cosmos, helping to set how many stars a galaxy ever makes, and therefore, over the long run, how many suns and worlds and chances at life a whole region of the universe gets to hold. The story of the biggest black holes is quietly a story about why galaxies, including our own, turned out the way they did. Let me leave you with what is actually secure, so the uncertainty does not swallow the wonder. It is beyond doubt that black holes of several billion solar masses exist. We have watched stars orbit them, and we have photographed one of their shadows. It is very strongly supported that black holes of a few tens of billions of solar masses exist in the great quasars and the hearts of the largest galaxies, even if their exact weights stay slippery, and it remains genuinely unsettled whether anything truly reaches 100 billion, whether such a mass is even physically allowed, and how the earliest giants were assembled so impossibly fast in the young universe. Those are not gaps to be embarrassed about. They are the live edge of the science, the place where the next answer will come from. And there are real ways that answer could arrive. A new generation of the Event Horizon Telescope is being built, with more dishes and sharper vision, aiming to capture the shadows of more black holes and to measure their sizes, and so their masses, more directly than any trick of light allows. Enormous new telescopes on the ground and a wave of sky surveying instruments will chart how vigorously thousands of distant galaxies are stirred, tightening the very scaling relations that handed Phoenix A its uncertain crown. We have, in fact, already proven the core idea works, just at the small end of the scale. Since 2015, detectors on the ground have been catching the gravitational waves thrown off when stellar black holes, the little ones weighing a few tens of suns, spiral inward and smash together. From the precise rising shape of each wave, physicists read off the masses of both black holes directly, weighing them by the quivering of space itself, with no light involved at all. It is a completely independent way of putting a black hole on a scale, and it has already weighed dozens of them. The dream now is to build instruments vast enough to hear the same kind of signal from the giants. And perhaps most tantalizing of all, when two supermassive black holes finally spiral together and merge, they shake the fabric of space itself, sending out ripples we call gravitational waves, and a coming generation of detectors built to fly in space is being designed to catch exactly those ripples. The pitch and strength of such a wave would read out the masses of the two merging black holes almost cleanly, weighed by the trembling of space rather than by any smear of color. When that day comes, we will weigh the giants in a genuinely new way, and we will finally learn whether the record numbers were honest or inflated. The argument we have followed all the way through this documentary is not permanent. It is simply where the frontier stands tonight. In fact, one of those new windows has already cracked open. In 2023, after years of patient effort, several teams announced that the whole sky appears to be humming with gravitational waves at extraordinarily low frequencies, a slow background rumble in the fabric of space, most naturally explained by countless pairs of supermassive black holes circling each other in the hearts of merged galaxies all across the universe. And they sensed it in one of the most beautiful ways imaginable. They used dead stars as clocks. Scattered through our galaxy are pulsars, the fast-spinning cores of dead stars that sweep beams of radio waves past us with almost unbelievable regularity, ticking like natural metronomes. As a gravitational wave rolls slowly through, it gently stretches and squeezes the space between us and each pulsar, nudging its ticks a hair early or a hair late. By watching an array of these pulsars for many years and teasing out the shared pattern hidden in their tiny timing shifts, astronomers picked up the collective murmur of the largest black holes in the act of pairing off. We have, in other words, already begun to hear the giants, even in places where we cannot see or weigh a single one of them. And every one of those slow, distant mergers is another giant growing heavier, another step in the long assembly of the very record holders we have spent this whole journey chasing. And that is the thing I keep returning to. 10 billion years ago, before there was an Earth for anyone to stand on, light left a whirlpool of gas around a black hole so large that our entire solar system would cross its edge only 40 times over. That light traveled the whole age of our planet to arrive here, and we caught it. And from a single faint smudge, we reconstructed the weight of the darkness at its center, and we argued about it, and we found the place where our own physics runs out. The largest black hole in the universe is not really an object waiting at the end of a list. It is an argument still underway between a spectrum, a scaling law, and a limit. And the most astonishing thing in the whole story may not be the monster at all. It may be that a species on one small world learned how to weigh the heaviest shadows in creation from nothing but the color and the timing of their light.